Welcome back, everyone. In this video, I'll be continuing the limit definition of the derivative section. Where we left off, we were computing derivatives by the limit definition. And the next one we had to do, we had to figure out f prime of a if f of x equals 1 over the square root of x plus 2. All right, so how are we going to do this? Which limit definition do we want to use? Because we have a radical, again, I'm going to use the one where we take the limit as x goes to a. And that's inside we have f of x minus f of a over x minus a. And this equals f prime of a. So when we do that limit, we will be done. All right, let's go ahead and just plug it in. Limit as x goes to a. X minus a on the bottom, that's sticking around. F of x is exactly this, 1 over the square root of x plus 2 minus 1 over the square root of a plus 2, because we're just plugging in a for x. All right, this looks pretty messy. Why does it look more messy than normal? Well, it's because these are in a fraction on the top. If this was just the square root of x minus 2 minus the square root of a, or sorry, the square root of x plus 2 minus square root of a plus 2, we would just rationalize immediately. And because it's square roots, we wouldn't have the trouble we had with the previous problem. However, they are in the denominator. So how are we going to fix this? Well, the best thing to do anytime you have a fraction inside a fraction is to get rid of the fraction. How can we get rid of the fraction here? Well, if we multiply by the greatest common denominator, which would be the square root of x plus 2 times the square root of a plus 2, because these have nothing in common, so we just have to multiply both of them. As long as we multiply that on the bottom as well, which is what I'm going to do, we keep our equation balanced, and we'll get rid of that fraction. Now, fair warning, it's going to look pretty messy, but this is the way we got to do it. All right, so on the bottom, I'm just going to go ahead and do what we always do when we're talking about the denominator of a limit. It's best just to leave it factored. In fact, in general, it's just best to leave things factored when you're doing limits. So we have x minus a times square root of x plus 2 times square root of a plus 2. Now, when we distribute this on the top, what happens is the x square root of x plus 2 cancels with this, and the first term is just square root of a plus 2. And we have our minus, and then we distribute both these to the second fraction here. The square root of a plus 2's cancel, and we have the square root of x plus 2. We're just sitting right here. Now, right now, this problem looks a lot messy than, a normal one, but we accomplished one thing very important. We don't have a fraction on the top anymore. We just have what's displayed here. So what do we want to do now? Well, that's what we hope to do in the first place, which is rationalize and simplify. If we want to get rid of the radicals here, which is our goal, we want to go ahead and multiply by what we rationalize by, and we just change the minus to a plus. Okay, so we're going to multiply by square root of a plus 2 plus the square root of x plus 2. And what we do to the top, we must do to the bottom. So let me go ahead and just write that in. And I know this is probably looking pretty messy, and I would agree. It's looking pretty messy, but we will see why this works so well. All right, so let's go ahead and see what we got. We got the limit as x goes to a. That denominator, like we've been mentioning, it's factored. Just leave it factored. We're going to have 4 factors: x minus a, this one, and this one as well. So let's go ahead and just write them all in. And the square root of a plus 2 plus the square root of x plus 2. But that's our denominator. But once again, we don't want to bother doing anything. Just leave it factored. Now what happens in the numerator? Well, we've done this quite a few times. So we know when we FOIL this, the square root of a plus 2's, the square roots go away, and we just get a plus 2. Now when we do the insides, we get square root of a plus 2 times square root of x plus 2. When we do the insides, we get the same thing but a minus because of the minus there. So we get minus square root of a plus 2 times the square root of x plus 2. And then the last, we got negative square root of x plus 2 times positive square root of x plus 2. The square root will go away because the inside's the same, but we have a minus. So we got the minus. And because we're subtracting, you got to be careful about distributing. We need to have parentheses around the x plus 2. All right, now what you should notice happen immediately is what always happens when we rationalize, and that's the middle terms go away. Now, what are we left with on the top? Because once again, we're not trying to do anything to the bottom until we can cancel. Well, on the top, we have a plus 2. And then if we distribute the minus sign here, we have minus x minus 2. And we have over this whole thing that looks pretty messy at this point, x minus a times the square root of x plus 2 times the square root of a plus 2 times the square root of a plus 2 plus the square root of x plus 2. And on the numerator, we can cancel out the 2 and the minus 2. So just to make this a little neater and not have to write everything over again, what are we left with? A minus x. I'm just going to rewrite it right next to each other, just to make it look a little neater. And why is having a minus x useful? You'll notice that we don't have anything matching on the bottom, but x minus a and a minus x are just flipped from each other, right? If we had the x in front and the a in the back, it would be fine. Well, you should have seen this plenty of times before when we have two things that are matching, but the order's just reversed like this. We have a minus in between. They simplify and cancel each other out, but they're off by a negative sign. So we can cancel these out as long as we make up for it by putting a negative sign in front. Right? And I can just show you on the side real quickly, a over x over a minus x over x minus a. If I take out a negative here, what's going to happen is I'm going to have negative a plus x. And I can just rewrite the negative a plus x as x minus a. And the x minus a's would cancel, and I'm left with that negative sign that I accounted for. So I have a negative sign here. Because everything else went away in the numerator, I got to make sure I leave a 1. But now that we've got that canceling, we can finally plug in x as a, our limit. We got negative 1 on the top. I'm going to plug in a right now. The bottom here, we have all these radicals. Everywhere we see x, we want to plug in a. The first one, we have the square root of a plus 2. Now the next one is already square root of a plus 2. Well, we'll just write that. And then parentheses, and then we have another square root of a plus 2 plus, and then the x becomes an a. We have another square root of a plus 2. So we just wrote a plus 2, the square root of that 4 times, but keep track of what's going on. We have a multiplication here, and we have an addition here. When we have addition, we know that that's 2 of them. So to simplify, I'm not going to actually simplify this part yet. I'm just going to make this 2 of them. We got the square root of a plus 2 times the square root of a plus 2, and then times 2 times the square root of a plus 2, because I have 2 of them inside. That's what the parentheses becomes. And now I can finally write my final answer. Negative 1 over, I have a 2. When we multiply something by itself 3 times, that's what we're going to get if we cube it. That's the square root of a plus 2 cubed. Now this is a mighty fine answer. You don't really need to change this, but you might see it written slightly differently because the square root is the same as the 1/2 power. So no harm in stopping there, but just in case you get it wrong and then you don't see anything that looks like this at all in your answer, it's probably written like this: a plus 2 to the 3/2, because the square root is the 1/2 power, and 1/2 times 3 is 3/2. But either of these two works great. Right. Now, once again, the number 2 and 3 that we did here for this part, they're the ones that are fundamentally more challenging than most of the examples, which are like number 1. The ones that are like number 1, when you have just a polynomial, you only have whole number powers of x. Yeah, it's kind of lengthy, but there's not a terrible amount of algebra going on. When you have rational powers, it's a lot messier. Right? But let me go ahead and just box that in to make it clear that this is the answer. Either one of these is f prime of a. Right, so the last portion of this section is the graph of f and then the graph of f prime. We want to just really take time to understand a couple things. If we're looking at the graph of y equals f of x, can we sort of draw what the derivative looks like? And the answer to that is yes, we will actually be able to draw it a little bit. And the reason is because the derivative is analogous to the slope of a line. And remember, when a function is increasing, that means it's going up as we move left to right. So I'm going to go ahead and highlight on this graph. On the graph of f here, it's increasing along this section until we get to the top. Well, is the slope there, if this was a line, would the slope here be positive or negative? And hopefully you said positive, and you would be correct. The reason why the slope is positive is because if you graph any line with a positive slope, as you move from left to right, it goes up. And we can go ahead and just confirm that by graphing an example. Let's just say y equals 2x. That slopes 2, that's positive. What does it look like? Well, as we move left to right, it is increasing, it's going up. All right, so anytime the graph is increasing, the slope is positive, but instead of slope, we're going to use the derivative. So the derivative is positive. Now, similarly, when this graph is decreasing, so if it's going down as you move from left to right, that is called decreasing. And decreasing, that's analogous to a slope being negative. And I could just take the same example, but instead of y equals 2x, do y equals negative 2x, and you can see as we move to the right from the left, we move down. Now, pretty much anywhere where a graph switches from increasing to decreasing, it's level or stationary or pausing. So many words to describe it, but the slope right there, f prime of x, is 0. So anytime you have a maximum, what looks like a maximum, the top of a hill, or the minimum, the bottom of a valley like this, at these points, the slope is 0. And really, when you sketch the graphs of derivative, you base it around where the slope is 0. Okay, so this is just a little chart to help you remember, but it's also very important. If the function's increasing, the derivative's positive. If the function's decreasing, the derivative's negative. And if the function is kind of stationary, level, flat, whatever you want to think about it, the derivative is 0. But often on graphs, it looks like tops of the hills, bottom of the valleys. All right, so what I'm going to do here is show you on this graph how we can sketch the derivative. And as I have outlined, it says, in general, you cannot draw the derivative with complete accuracy. The reason is you won't have the numbers. So I intentionally did not label numbers on this graph. I just have the graph shape. It's going up and then down and then back up. It's pretty much the same graph as above. However, the further the slope is away from 0, that means the steeper the graph is. That means the farther away from the x-axis it will be. Now, just to relate this back to lines, y equals 2x has slope 2. Y equals 3x has slope 3, and a slope that's bigger is more steep. So if your graph gets really steep, the slope is getting bigger. And if it's flattening out, so like y equals 1x, then it's more flat, it's less steep. That's just helpful to know how to really sketch it a little better than before. So just knowing that positive, negative, or 0 is good. And if we want to take it one step further, we'll use that idea. All right, so how do I want to graph this? Well, first off, I'm going to look for these maximum minimums, the tops of the hills, the bottom of the valleys. And for this function, I have 2 right here. Well, at these points, my derivative is 0. What I'm going to do when I start sketching the derivative, I'm not going to just freehand it. I'm actually going to plot 2 points for the derivative. Being 0 means they're on the x-axis. Right, so directly below and above are 2 points on my derivative. All right, now just because we have the two zeros here of the derivative, it's kind of easiest if you start off in between. What's happening to the graph in between the maximum and minimum, between the top and the bottom? It's going down, it's decreasing. Okay, so between these 2 points here, our graph is decreasing. I'll abbreviate it DEC. Now, what does that mean? That means the derivative is negative. Negative means it's going to be below the x-axis. So as long as I draw this below the x-axis, it doesn't matter how well I draw it because I can't draw it super well. So I'm just going to draw it something like this, because I need it to come back up to hit 0 at this point, but I need it to be below the x-axis the entire time. Right? It's decreasing the entire time between these 2 points. So the points I plotted with 0 right there, gonna be below the x-axis the whole way. Now what's happening to the right? So starting here, is my graph as I move to the right increasing or decreasing? And what you want to notice, it is increasing. Since it is increasing, that means the derivative is going to be positive, so it's going to come above the x-axis. Now this is the one thing that it's really hard to do, and it's really hard to get used to, and it'll just take time. But when the graph stops bending and just looks straight, like it looks flat like this, that means the slope is just staying the same number. So it actually will sort of flatten out, but it'll stay above the x-axis. All right. Now, once again, you don't have to draw these very accurately. And for the most part, I would just be looking for, do you have these zeros? Do you have where it's decreasing? And do you have where it's increasing? That's the most important thing. But I just want to add in a slightly more detail. Now back here, remember for increasing and decreasing, we always look left to right, and it's also increasing over here, which means the graph is going to be above the x-axis when we're back here. And once again, you can't really be too accurate. It might look like this, it might be flatter, but as long as it's above the x-axis, that's telling us it's increasing. All right, so the graph of f prime would look something like that. All right, the next one, I just wanted to use a visual example that says the graph below represents the height of a ball thrown in the air, h, in feet after t seconds. So you throw a ball in the air, it's going up, then it's coming back down. Now this is just representing the time. So it's telling you it's going up as time goes forward, and then eventually it gets to the top, the ball, and then it starts to fall down. It says roughly sketch the velocity. Since this is a position, it's a visual thing, the velocity is the derivative on the same graph, and then answer the question below. So let's roughly sketch the velocity. Well, what's happening at this point? What do we always want to look for when we sketch the derivative? We want to look for the points where it's 0. And where it looks flat, where it's at the top up here, I labeled as 3 to make it easier for you. This is where the derivative is 0, because we're at the top. Now, what are we doing to the left? It's increasing, although it's eventually going to slow down because it's got to hit 0. So it's increasing, which means it's above the x-axis, but it's slowing down. So it's going towards 0. Once again, as long as you have some sort of shape up here that's above and is going towards this point while it's above the x-axis the whole way, that's the important thing. Now what's happening to the right? So starting from here, we start decreasing. Now this one is barely decreasing, but it starts to decrease faster and faster, which means as we move more and more to the right, it's going to get more and more negative. So it probably looks something like that. And that's our h prime, which is our velocity. Now it doesn't have to be a perfect line. It might not be a perfect line. I'm just estimating because that's all I can do. Now it says, based on your drawing of the velocity, how would you interpret v of 3? Well, we kind of figured out from the beginning, but definitely with the graph of our velocity v of 3 is 0 because it's on the t-axis. V of 3 equals 0 means after 3 seconds, the velocity of the ball, right? Because it's a ball thrown in the air, is 0 feet per second. Okay, the velocity of the ball is 0 feet per second. Remember, velocity gives you the derivative, which is the rate of change. And what's changing is feet over time, feet over seconds. Well, if the velocity of the ball is 0 feet per second, that's really where the ball is stopped. That's really where it's at its peak. It had been going up, then it stopped for just a very, very brief moment, and then it's falling down. This is the 3 seconds is where it's stopped. So a big really portion of understanding the derivative is also being able to graph it, but it is very, very challenging. I understand that. So we don't want to go into too much detail, but if you can get a rough sketch of the graph, that means you understand what the derivative is saying. And that's probably the most important part of this section. All right, so the last thing in this section, and then we'll finally be done. What kind of points on the graph are not continuous? So if you have a graph of f, which is what this represents, where is it not differentiable? Well, there's 3 points, kind of points where you always are not differentiable. One is when it's not continuous. Remember way back, the very first words in this section to define the derivative was that the function has to be continuous. So if it's not continuous, there's not a derivative. Let's say this is x equals a right here. This is not continuous because there's a gap, it's a jump. We would say that f prime of a is d and e. And that's because the derivative does not exist because it's not continuous. It is a requirement for the derivative. All right, what other kind of points are not differentiable? Well, pretty much anywhere a graph is smooth. So all along here would be differentiable until we get to this point. And then after the open circle here, as we're going, it would be differentiable. But one problem is that if the tangent line is vertical, which means the slope is basically infinity, it's not differentiable. So if you have a function which looks like it's vertical, the tangent line would be vertical as well. And that this point that I highlighted here is really where that's happening. The derivative is infinite, so it's d and e. Let's call this number b here. F prime of v is infinite. So the way we write that is it does not exist. So pretty much the only time we use infinity or negative infinity is when we're talking about limits. With derivatives, not that useful. All right, the other kind of point is one where you have a sharp point. And that's going to look a lot like, it looks like you have 2 lines coming to a point on your graph. I'll call this C here. It's a sharp point. It pretty much looks like a V. And the reason that it's not differentiable there is you really need a smooth graph. So what we would say here is f prime of C also does not exist. Now, a classic example of a sharp point is the absolute value graph. What I'm going to do is just graph it for you. Y equals the absolute value of x, the way you type in absolute value in most calculators, ABS, and you see that we have a sharp point there. Now, the reason this isn't differentiable is we have a line on the left, its slope is -1. Right? You can figure that out because it starts in the origin and it intersects as 0.55. It's a straight line, which means you can use your old slope formula and you'll get -1. Well, the slope on the right side is +1. So what's happening down here at the sharp point is we have one side, the slope is -1, one side, the slope is +1. If they're not the same, then it's not differentiable. Same reason why a limit has to have the same one-sided limits. At a sharp point, your slopes on each side are not the same, which is why it's not differentiable. Right? Hopefully, at this point, you have a good understanding of what the derivative is saying. It's important to practice not only the definition of the derivative, but understand what it means, what it looks like visually. And luckily, in the next section, we will create formulas that make computing derivatives a lot easier. I'll see you there.